Just giving people one more minute. At least one more coming. That's good. Okay. Welcome back from lunch. Welcome back to the conference program. This session is the first of two sessions on advanced applications. In this session, we're going to hear about quite a nice spread of different aspects of large applications and how to support them on the networks. We have a talk on the very large volumes of data being produced and how to store and manage that data. We have a talk on how to effectively and efficiently ensure that the right network connectivity is in place at the right time and at the right moment, in the right place for supporting large applications. And we have a talk on how we as European NRENs and as the European NREN community can effectively and efficiently support such applications and help them with the requirements. The first speaker is Hanno Holties. He's a system engineer at Astron, Radio Astronomy Observatory Division. He's been leading efforts for the LOFAR and VSRTG radio telescopes. And since 2008, he's been the project manager for the LOFAR efforts there. He will talk to us about the LOFAR radio telescope that's been deployed in 5 countries and how to manage the very large volumes of data being produced by that. So, Hanno.
Thank you, Lars. Okay, thanks for joining me here in the room. This presentation will be about the LOFAR long-term archive, where archive suggests it's only static data. It's actually more than that, but I'll come to that later in the talk. The subtitle, therefore, is a bit better, actually. A distributed information system for radio astronomical data. I believe this is the first time, I'm not entirely sure, but that a presentation about LOFAR has been given here at the Terrena conference, so I'll quickly go through what is LOFAR and what the system look like, what are the networking challenges in particular. LOFAR is a European scale radio telescope. It consists of 48 stations. There will be 48 stations later this year, of which 40 are in the Netherlands and 8 are abroad, 5 in Germany, 1 in all of UK, France and Sweden. It is new and unique in its size, in the sensitivity that it will achieve, but also in the frequency range. There's only very few radio telescopes that can observe below 250 megahertz, and will do it at very high sensitivity. It's operated from a place called Dwingelo. It's in the Netherlands. It's in the, for Netherlands terms, remote area, and it has a distributed data storage and data processing system. This is an overview, if you like, of the LOFAR telescope. This is the pointer? Yeah. So here in the northeastern part of the Netherlands, there's the center of LOFAR. It's a rural area. It's relatively radio quiet. And that's where most of the LOFAR stations are placed. Here at the blue dot, actually, there's Groningen. That's the compute center of the University of Groningen. That's where we collect our data, not only of the Dutch stations, but also of the stations placed in several sites in Europe. Each LOFAR station consists of a large number of relatively simple antennas. There are 48 stations, already mentioned that. And each station has 2 types of antennas. There are in total 5,000 low-band antennas, which can observe, find radio data in below 100 megahertz. And there's 3,000 high-band antenna tiles, where each tile has 16 antennas actually, and that can observe between, say, 110 and 250 megahertz. They're divided over the 48 stations, and at the very center of the LOFAR telescope, there's what we call the superterp. Basically it's an island where 6 closely packed stations are placed, and that's really the center of the LOFAR telescope. And there's actually 3 configurations of stations. This is not so important for this talk, but this is a picture of an international station which is larger. It's more remote, but it's also larger. And this one is placed near Evelsberg, the radio telescope at Evelsberg. LOFAR is what we call SKA Pathfinder. The SKA, probably mentioned before, you probably have heard of it before, Square Kilometer Array. It will be the next generation radio telescope. It will generate data and require information technology, say, a factor of 100 more than LOFAR will. But the general principle of the SKA, which will be built in the coming decade, is very much the same as LOFAR. So LOFAR is a good playing ground, test ground, if you like, for SKA technology. The SKA is actually a global world-wide collaboration, so it's even more challenging than LOFAR. I won't go into detail about what a radio telescope does, how it works. Jive has presented here in the past. I'm not sure if Paul will say more in the next talk. I know that Kees yesterday mentioned a little bit about the radio telescopes and how they work. For now, I'll just say that the LOFAR telescope has a number of levels at which data is collected and processed, analyzed. And at each level, we actually try to scale down the amount of data, and you'll see that going from one level to the other will reduce the volumes of the data, which is necessary because otherwise we wouldn't be able to handle all the data. But also with the different levels, we have levels of beamforming, what we call beamforming. Already mentioned that the antennas for LOFAR, the dipoles, are very simple. They're basically electric wires, and they sense almost all of the radio waves coming in from the sky, any visible part of the sky. So the antenna beam, the part of the sky that the antenna sees, is very wide. It's almost half a sphere. What we do at the station level, we combine the signals of all the antenna dipoles, and we coherently add them up to form what we call a station beam. That's already, well, with this processing, we can make the added signal of the antennas point to a certain part of the sky. So the telescope as a whole becomes sensitive for a certain direction. At station level, this is, we have a visibility area that we see of order of degrees. And if we combine all the signals from all the stations over Europe, and we do the same kind of processing, we would be able to form beams which are 1,000, 10,000 times smaller again. That's what we call tight array beams. So why do we have to have all these stations divided over Europe? That has to do with the resolution, how sharp a picture we can make of parts of the radio sky, if you like. A couple of slides on the science that we can do with LOFAR. One of the main drivers for the LOFAR telescope is its sensitivity, and it will allow us to look back in time, very close to the origin of the universe, the Big Bang. This slide actually was shown this morning as well in the talk about the LHC by Ian. And there the LHC, they're concentrating on the very early part of the very early stage of the after the Big Bang, something you won't be able to see with telescopes. But LOFAR will be looking at an area which is very close to, or is about what's at the edge of what a radio telescope can see. And basically it's looking back at the time when the light was switched on, if you like, in the universe. When the cold gas, which had formed out of the Big Bang, formed stars and heated up the gas and started emitting radio waves in the megahertz and gigahertz range. And that's what we're observing with LOFAR. There is what we call a key science project for the epoch of reionization, trying to reconstruct an image of that part of that era of the universe, and in total, to be able to extract the signal and get the best picture, if you like, of the epoch of reionization. A total of 1.5 petabyte of data will be collected over a course of years, a number of years, and quite some processing power will be needed to analyze the data into an image, if you like, and into information about the early stage of the universe. And for this processing, actually, a special purpose GPU cluster has been acquired, which is placed in Groningen. Another strong point of LOFAR, because all the antennas basically see all of the sky, is surveys. We can relatively quickly do surveys, and this is a new era for telescopes, this range of radio frequencies. So we can effectively do surveys. We expect to observe many sources, up to millions and billions of new stars, not so much stars, but objects in the sky that emit radio waves we expect to find. And over the course of the existence of LOFAR, if we want to do a full sky survey, we'll produce many petabytes of data in collecting all the information and finding the new sources. Another unique capability of the LOFAR telescope is that, again, it sees all of the sky, and we can use it as a radio sky monitor. We can form beams, we can look at certain parts of the sky, but if anything is happening in a certain area, we can quickly direct one beam, a part of the system, to that area, so we can have large areas that we monitor at relatively low sensitivity, and if something interesting is happening, we concentrate our sensitivity, our capability on that area. And we can also follow up on events that are gathered from satellites and other telescopes. As said here, basically only data transport and processing power prevent us from monitoring the entire sky continuously. As you'll see, that is a bit too much to ask for now. This is another application where we'll also be producing, if we do the beamforming observations, up to tens of terabytes per hour with LOFAR. And finally, a kind of science is cosmic rays. LOFAR can detect cosmic rays, high energy particles hitting the atmosphere of the Earth and producing, amongst other things, radio waves. And those are very short events, of course, and for that, LOFAR is equipped with on-station memory, in total order of a number of terabytes of memory, which can buffer data, raw antenna digitized data at station level. And if something interesting is happening, we can freeze the buffers, and we have about a second of time that we can look back in time to reconstruct an event which has caused radio waves to go through the sky. And there's more applications, cosmic magnetism, solar system, space weather, etc. I'll not go into those. Finally, LOFAR is in many senses an IT telescope. It provides a certain infrastructure, networking infrastructure, computer infrastructure. And astronomy is not the only application that can benefit from that. So there are other applications that are using the same infrastructure for their purposes. Infrasound, precision agricultural, we're in a rural area of the Netherlands, geophysics, and the geophysics, for example, is interesting for that part of the area because natural gas is being collected there, and that causes minor tremors and settling of the Earth. And the company wants to know exactly what the consequences are. Okay, looking into the LOFAR network. This is an overview of what we have or almost have for LOFAR in place. Most of this is in place. I'll quickly go through the 4 levels of data analysis that we have. Bottom part, there are the stations, of which I've shown you the pictures. And if you add up all the digitized data of the antennas, you have a total raw signal of about 500 gigabit per second per station. So if you would add it up, it would amount to 240 petabytes per day. That we cannot collect or store in any way. So we have at the station level already a first processing facility and the storage buffers, which I've mentioned before. And the processing is basically to form beams, to select data for a certain area of the sky. After the beam forming, we still have quite a lot of data, but per station we have 3 gigabits per second. In total for our stations, close to 200 gigabit per second we can collect. That is sent to Groningen. Groningen, there's where we have our supercomputer, IBM Blue Gene P, and compute clusters. And the supercomputer handles the online, the real-time data. It takes the input from the stations and does real-time processing, like correlation, beamforming, system-level beamforming. And after that processing, we still have a data stream of up to 80 gigabit per second actually, but in practice we expect the mode to be limited to 60, 70 gigabit per second. That still is 650 terabytes each day. In our central processing facility, we have storage systems to which the online system is writing its data. And the total capacity that we have there at the moment is 2.5 petabytes. Well, if you fill it at 600 or more terabytes, it will be filled after a couple of days already, and that has always been the model. This storage is meant only for temporary storage, say up to 1 or 2 weeks. We don't continuously observe at the maximum capacity, so we expect to be able to store up to 2 weeks of raw data. The data is there. It's still way too much to store for long term. So we need to analyze it, reduce it in volume further. And for that we have science pipelines running on our own Linux cluster, which is also in Groningen. Total capacity of that is about 25 teraflops. And those science pipelines will, again, reduce data, filter out all the uninteresting data, if you like, flag the bad data, do the quality assessment to check which data we want to store for longer term. Peak output of the system as a whole to the long-term storage is expected to be 20 gigabit per second, still 200 terabytes a day. And actually, we also have an offload mode. If central processing systems are overloaded, we have a very intensive observing campaign. We have a capability of actually storing our data not on our own systems, but transfer them to one of the long-term archive sites at 60 gigabit per second, which is approximately observing speed. So then we come to the long-term archive, and actually that's my area where I'm working in and where the rest of the talk will be about. It's called the long-term archive. It takes care of long-term storage of all data products that have science value, if you like, and that have been checked for quality and reduced sufficiently in volume. It handles distribution to the users, so all our scientists, the astronomers, will get the data through the archive. They will not be working directly logging into the central processing systems. And it also will provide bulk data processing facilities. And in that sense, it's very much like the mega data centers which have been presented earlier this week as a vision for the future. I think that model actually fits what we do for LOFAR. We have a couple of sites. At the moment we have Groningen, Amsterdam and Jülich in Germany, where we do the long-term storage, where we do the bulk data processing, and well, still we are producing into the archive up to 5 petabytes per year. That's what we expect at the moment at least. And data volumes, data sets of tens of terabytes, that's not what a regular astronomer can handle on his own workstation or even on university computer clusters. So we want to provide central services for that, where we have pipelines running. Already mentioned before, also we will allow offloading, that will be temporary storage of raw data to level the peaks in central processing. We use disk and tape technology. Tape, total cost of ownership is still the lowest, so we are taking that into account. And also for our users, traditionally astronomers ask for observing time at a telescope. In the LOFAR case, they will also ask for long-term storage capacity, which is allocated to them. One project which plays an important role here is the Target Project. University of Groningen, IBM, Oracle, some other partners are involved in that. And that is looking at data information systems to handle sensor data. So it's about streaming processing from sensors into storage and also automated offline processing, databases, etc., to the user. For LOFAR, this is an opportunity to develop some of our information challenges, and the target system provides a platform with different pools, different types of storage, some about low latency, others about bulk storage and streaming data, also tape storage, and this is for us a playing ground to see how can we handle in a petabyte scale data center with terabyte size data volumes, how can we handle that efficiently? And this is where we try out our placement policies and handling policies, etc. Current capacity for the long-term archive in Amsterdam at SARA, we have a petabyte of tape storage, about 300 terabytes of disk storage, of which we use 250 terabytes. That's mainly been generated in the past half year or so, and that is scaling up in the coming year. At Jülich, we've only just started transferring our first data sets. There is a petabyte of space, of tape space available. At the moment, we've filled only 10 terabytes, but we're already using it as a distribution facility to our German, to the German astronomers. In Groningen, the target systems, that's just been through an acquisition round, and it will grow basically now up to a petabyte, more than a petabyte disk storage, and more than 3 petabytes of tape storage. All these sites provide computing facilities as well, so they're large clusters, in particular in Amsterdam, and of course in Jülich, which is the largest compute center, and we also are working on a computer cluster in Groningen. We've gone through data challenges. This morning was more and more about LHC data challenges. We're not quite at that level, but also generating a lot. We have sustained input to the archive of 400 megabytes per second. We have achieved peak rates of up to 900 megabytes per second, and then we get close to what can be achieved on our 10 gigabit per second connections. This is the LOFAR long-term archive operational model. In view of time, I won't spend too much on it because it comes back, but basically we have some central services, in particular ScienceVO portal, what the astronomers will be working with to find their data, locate the data, but if there's any interaction with bulk data, that will happen directly at one of the long-term archive sites. We've set up the archive sites in such a way that there's a relation between the site and the community. So all our key science projects are primarily associated with one of the sites, where we store, say, the primary copy, which is kept online for a certain period as well. If data is found to be important to take real good care of, we'll also store a secondary copy at one of the other sites. So that takes care immediately of the geographical separation. The philosophy is to store data where processing is expected, but we can't guarantee that processing will only happen at the place where we think it will happen. We're currently working on porting our pipelines to the systems everywhere. This is quite a challenge. So actually, in this distributed system, the network between the sites is becoming a bit of a bottleneck to allow, until we have pipelines running everywhere, which is costly as well in terms of development. Network actually limits us moving the data around in any way we want. This is what we have. We have the central processing area with 10 gigabits per second connections to Amsterdam and Jülich, and because it's basically in the same room, we have a 60 gigabit per second connection to the target storage, which we will be using for this offload mode. Any other connections between the sites and from the sites to the users at the moment are existing NWAN infrastructure, shared infrastructure. Wouldn't it be nice if we had, would be able to upgrade all the networks that we have between our sites, networks at the bandwidth at which we are producing data, which would not only allow us to offload our data anywhere in the archive, but would also allow us to do the processing that we now need to do on the central processing systems transparently anywhere in the archive. And then it would also be very nice if the users could have a very good access, say with light paths or 10 gigabit per second to their data. But we don't have the funding for that, and I don't think the environmental people, including me, will be very enthusiastic about it as well. So what is a good alternative? I think the light path technology and bandwidth on demand is actually a very good alternative that would allow LOFAR operations in the long-term archive to the extent that it will work very well. It's just, I'm not sure how well this is visible. This is a very, well, bit of a movie. We can use bandwidth connectivity for to allow users, if they want to retrieve a large data set, they could use a temporary line. If we want to do remote processing, we have a data set here, but we have the processing facility somewhere else. We would be able to set up a high bandwidth line to there. etc. Offloading of data would be enabled as well. So, getting to the conclusion of the talk, what are our developments and what are our challenges? At the moment, we are collaborating in the NEXPReS project. Paul Boven will talk about that in the next presentation, where LOFAR is interested in prototyping and working with bandwidth on-demand technology and also working with network storage. But we see some challenges actually that will not be covered by that project and for which we will look for future opportunities, including use patterns, data management, petabyte scale, tens of terabytes data sets. It's quite a challenge. It's not done before. 10 gigabit per second operational data flows, streaming processing at these high data rates, workflows over the wide area network, and coordinated scaling, because in this case, all the resources need to be matched. The computing, storage, and network need to be lined up at the same time. And the developments that I've heard at this meeting actually sound very interesting to LOFAR there. When I sent in the abstracts, I was explicitly asked to say a couple of words about lessons learned. What can other communities learn from LOFAR? This is just a list. There's of course far more. This is a list with which I came up this morning or yesterday evening. Our lessons so far: do not reinvent the wheel if you do not have to. Collaborate. I'm very happy that the LHC has gone as far as it has already, because we're using much of their technology. The downside to that, of course, is that they have developed it for their application, and it's not always fitting to LOFAR. And also be very careful with bleeding-edge third-party solutions. They'll sometimes actually cost more work and time than they have benefit for. But identify the unique issues, the unique characteristics of your application, and concentrate on those. Some for LOFAR are the large data sets. We require large scratch space on the computing areas, for example. We require large multi-core queues. They are not standard facilities in the grid environment. And that's what we've run into. Also, we've chosen to manage our own file catalog and metadata. That's our core business. And what's been provided by other partners does not ideally fit our purposes. Also, get your users on board, provide an incentive for them to move to new technology. We found that if there's a hurdle or if technology is not very mature and it's changing still, it's very difficult to get users to move to this new technology. So involve them in mini projects that provide quick results, and don't shy away from low threshold solutions even if they're unconventional. Educate your users to prepare for the challenges. People are used to a certain way of working, and they won't all conclude right away themselves that a single group cannot solve all the problems. Actually, an application like LOFAR benefits from large infrastructure. Starting time, manage expectations. Both scientific R&D and realization of these cutting-edge IT technologies have a tendency to ignore planned dates, and that can be frustrating. Acknowledgements, you'll see the name, you can find them in the presentation. That's the end of my talk. Thank you. Any questions?
Any questions for Hanno? Well, I have one, partly because we have one of the users in our network, one of the sites contributing to this. It wasn't quite clear to me the bandwidth requirements you have for the users actually accessing the data. You talked a lot about the streaming of the observed data into the system, but how much data is being taken back out? How dynamic is it? Does the processing happen at your facility, or is it like with the LHC that users request all the data back out and do a lot of computations and submit it back in? How's that working?
That's a good question, and I've left it a bit in the middle because it's least well defined at the moment, I could say. But certainly in this stage of LOFAR, where we're commissioning our data, the pipelines, the processing software still needs to be developed. What we see is that our users do want the data sets on their own infrastructure, where they have full freedom to play with software, with data, etc. So at the moment, there are relatively many requests for large data sets to get to a university. As discussed in the architecture, we aim to have our most important pipelines available within the archive, so that data sets that they will be working on do not need to be moved. So expect that the data retrieval to end users would be an order of magnitude smaller than what we use internally, but it could still amount to relatively large.
Still on the gigabit scale.
Right. Yes, yes. Yeah.
With a question down there.
Alex Reed at Arnet. Can you tell us what the exact status is of the LOFAR at the moment? Are you actually collecting data? Are you full operational?
The LOFAR telescope operates. We are observing. We have, I think, 40 out of 48 out of the 48 stations operational. The main effort at the moment is going into our science pipelines to get the analysis of the data fully functional. The milestone for that is next September, when we will start a large campaign for observing data and analyzing it. We are doing some science already, but it's mainly commissioning what we do at the moment. And full operation, let's say, end of the year, early next year.
Right. Well, thank you, Hanno.
Yeah, thank you.
So as already indicated by Hanno, our next speaker is Paul Boven. Paul will talk to us. First, that Paul works at Jive. He's been working for quite a number of years as a system engineer and doing networking for VLBI. Before joining Jive, Paul worked for a number of years at Sarah, so he's intensely familiar with the requirements of the R&E space. He'll talk about the NEXPReS project, a project that takes on further the support for VLBI and eVLBI in Europe and beyond, and is in particular investigating the use of dynamic bandwidth commissioning and bandwidth on demand technologies for eVLBI. So, Paul?
Okay, thank you. My name is Paul Boven. I work at Jive. What you see over here is a little map showing some of the radio telescope we use in eVLBI, and I'll start with explaining what all these acronyms are meaning. Jive is the Joint Institute for VLBI in Europe, and our mission is to operate the EVN correlator, supporting astronomers who use it. And we are located in the same building as Astron, actually, in Dwingelo in the Netherlands. So then the next question, the EVN is a collaboration between many radio telescopes and astronomical institutes all over the world almost. And then that leaves us with one more question, which is, what is VLBI and eVLBI? For that we go a little bit into the science of it and the background of it. Most people who know about astronomy are imagining a telescope like this, a big tube that you use to look at the sky. And with this we can see light that our atmosphere happens to be transparent to the visible light. However, so higher frequencies are fortunately blocked, so we don't get all the dangerous radiation. We are protected. Our atmosphere protects us from dangerous radiation at these shorter wavelengths, and also at the lower infrared wavelengths. And then here is another hole in the spectrum, so to say. LOFAR operates at the lower end of it, VLBI and most radio astronomy at the higher end of it. And we use radio telescopes like this, a dish that collects the signal and focuses it. And one of the things that makes radio astronomy interesting is that we actually see completely different things than you see with an optical telescope. Of course, we still see the sun. It's one of the brightest sources in the sky, but unlike in the optical, the sky is actually more transparent at radio waves, and it doesn't really bother us that the sun is in the sky. The sky is still black where the sun is not shining. In the same way, clouds and rain do not bother us, which is one of the reasons that the Netherlands has mostly specialized in radio astronomy. And so what we do see is things like hydrogen. Sorry, that's the wrong button. Is hydrogen of our own galaxy, other galaxies. We see supernova. We see remnants of stars that have exploded in the past. We see active galactic nuclei, which are possibly black holes at the center of very far away galaxies. And one of the other things we are involved in is tracking spacecraft within our own solar system. So the antennas we use are a little bit bigger than the LOFAR antennas in the sense that the diameter of these is usually somewhere between 25 and 100 meters. And signal from a source very far away falls onto the parabolic surface of the mirror, is reflected to the focal point, maybe reflected once more, and there is a receiver, we record the data, and that's what we start to work with. So another comparison with optical astronomy. The resolution of a telescope basically depends on two things: the size of your telescope and the size of the waves that you're looking at. So for instance, for the Hubble telescope, if it's operating in visible light, say about 600 nanometer, it has a diameter of the main mirror of about 2.4 meters, which gives you about 0.06 arc seconds, which is fairly small resolution. Compare that to the radio telescope you see here. The radio telescope is actually 10 times bigger, but the radiation that we're looking at is at a wavelength that is 100,000 times larger. Therefore, the resolution of a single radio telescope is fairly poor. 600 arc seconds, that is actually, I think, that means that the full moon would only be 3 pixels on the sky. So you have very poor resolution. And if you actually wanted to have comparable resolution in optical and in radio astronomy, you would need, in the same formula, you would need a dish that has a diameter of about 240 kilometers, which is not really possible, of course. Fortunately, a number of rather intelligent English people came up with the idea of interferometry, where you take a number of telescopes and join them together and create a virtual radio telescope that has actually a resolution that depends on the distance between the longest telescopes. And then the more surface area all your telescopes together have, the better the image quality. And if all those telescopes are very far away from one another, it's still very important to get the timing as you need extremely accurate timing for that, which means that at each radio telescope we are using an atomic clock, a hydrogen maser, to timestamp the data as they come in. And then to actually turn this data into something that you can look at, into an image or a measurement, it needs to be processed in a special purpose supercomputer. This is our correlator at GÉANT. It's built on ASIC technology. It is about 14 years old now. And actually for years it's been the fastest computer in the Netherlands, provided you only want to do multiply numbers of 2 bits and then add them together. That's the only thing it can do, because it's built in ASICs. And that's also why it's still so fast that at that moment we cannot even afford, more than a decade later, to replace it, for instance, by a full cluster of PCs. Both from terms of space, cost, but also power usage. So the telescopes record the data at rates at this moment up to 1024 megabit per second. We store them on special purpose packs with 8 hard disks, and they get sent to GÉANT. This is a set of these disk packs. And actually this is our storage system. So Hanno was earlier talking about the petabytes that they are using. The EVN storage pool is about 1.7 petabyte, but ours is not in racks and turning and spinning. Ours is actually sitting idle in disks like that, and the disks are taken out of this storage system, run through the correlator, then they go back in here. And the storage system actually spans 2 floors. This is the lower, this is the basement, and there is another access point higher up. So what happens is the disk packs come to GÉANT, they get loaded, they get scanned, they're transported downstairs, and then they get processed. After this they get released and cleaned, and then the disk packs go back to the telescope. So our 1.7 petabyte is actually moving all over the world all the time. We have generally 3 observations per year, and they take about 3 or 4 weeks each. So when we started with VLBI, actually well before I joined GÉANT, we were using tapes like this, single reel tapes. Later, we started using hard disk. You have 8 hard disks in a carrier. This carrier is actually slit into a metal sleeve, goes into a box with foam, and then is mailed to a radio telescope, and then after a while we get it back again. And nowadays we're also doing this in real time over the network, eVLBI. And that's a fairly new development. I think we are seriously doing this now for about 4 years. What you see here is actually our connection to SurfNet. The yellow connection is a 10 gig interface, and all the orange ones are 1 gigabit light paths that connect into SurfNet, and from there on into into GÉANT, into Netherlight and other places all over the world. So we were actually observing yesterday and last night, started at about 11 with some tests, so you see lots of gaps here, where we are just testing different configurations, trying to get everything to work. You have to imagine this system was originally designed to work with tapes. We've then gotten it to work with hard disk, and now we get it to work with real-time data. And there's quite a few challenges in getting this to work. And then about here, the actual science part of the observation starts with each color representing a telescope. So this is Westerbork in the Netherlands, Onsala in Sweden, Medicina, Italy, Poland, Germany, Effelsberg. This is Jodrell Bank in the UK. This is Hartenbeesthoek, South Africa, and this is China, where we have a little bit less bandwidth available at the moment. And unfortunately, at this point, our cooling system died. And actually, that's a little bit to the left of it, and then all systems had to shut themselves down to prevent problems. People managed to get cooling working again. It was a very eventful night for the people in Dwingelo. And unfortunately, it happened again slightly after midnight. I guess it's a bit warmer in Holland than it is over here at the moment. And we had some severe issues getting stuff to start again before finishing the recording at 4 a.m. So this is a little overview of the network connections that we are able to use at the moment, thanks to the cooperations we have with the NRENs and also the NEXPReS project we did together in the past. So I've ordered them in longest distance over the net to the shortest in milliseconds. These are the country codes, these are the name of the observatories, and this is the bandwidth we have. And where it says R, it means routed. So this is over generic, but NREN and internet. Where it says VLAN, we have a VLAN capacity, and where it says LP, that means that's a light path. So we have a mix of light paths, VLANs, routed connections, and other things. And we even have a little bit of dark fiber between the Dutch telescopes in Westerbork, so that we're able to use two colors at the same time to get a little bit more bandwidth. And this is another image of how the network looks with Europe zoomed in a little bit. So Jive is over here, very close to Westerbork. You see the fibers coming in here, and you see all the telescopes around the world and all the different connections that we're able to use. So we've been doing network-based VLBI for a while. We call it eVLBI, and we've been doing disk-based VLBI for a bit longer. And it's interesting to compare, to contrast the two approaches. So if we do disk-based VLBI, we record locally at the telescope. That means that there is no limitation in how much bandwidth we can record. We can record up to the full system capacity. Whereas on eVLBI, when we're doing this streaming in real time, we are often limited by the connectivity of some of the stations. Some of the stations we can do the full 1024 megabit per second. Others we are limited to, say, the 1 gigabit per second that a light path is usually at this moment. And others we have even less capacity, as you saw in the previous slide. Shipping usually takes weeks. We gather a number of disk packs before we send them off so that we save on shipping costs. Whereas in eVLBI we can do this, you basically get it within a millisecond, because that's the time that the light needs to travel over the fibers from the radio telescope to us. In a sense, that's not so important, in that the signal has actually already been on its way for thousands or millions of years to get from the astronomical source to us. On the other hand, getting the signal in real time allows us to do quality checks you cannot do in any other way. Because we look at the combination, the correlation of signals between two telescopes. The signal from a single telescope has no real meaning for us. We need to be able to compare it with and correlate it against the signals of other telescopes to actually get our data product. So the real-time checks, quality checks we can do are very important. Disk-based VLBI, as I said, we have about 1.7 petabyte, and it's always a very big puzzle for each new observing session to see how much disk space we can allocate to the different experiments, and that is actually a limiting factor. Whereas when we do eVLBI, we can do it without ever hitting a disk until after it comes out of the correlator, and by then it's only a mere gigabytes, which is easily stored. Of course, both methods have their disadvantages. We have disks that end up broken or that we're unable to record, but we also have fibers that break, connections that go down, routers that are not cooperating just at the moment that you need them. So both of them have their drawbacks. For disk VLBI, we need to schedule long in advance in order to have enough disk capacity at the telescope for them to record on. Whereas the very interesting thing that you can do with eVLBI is called target of opportunity observations. We get a trigger signal from a gamma ray satellite, for instance, that sees a burst go off, and we are able to schedule an operation within just a number of days, because we just need to point the telescopes, get time on all the telescopes, and we can start processing the data. But in the end, because this has the full bandwidth at each station, disk-based VLBI has always the better sensitivity. But network-based VLBI, despite the problems we have with links going down and all that, has the better reliability. And the main reason for that is that we can do those checks that you need to do. If one of the stations has an atomic clock that is slightly off, if one of the stations is not exactly pointing at the right direction, the data looks completely correct until you start doing the comparison with all the other telescopes. So this actually allows us to, on the fly, do a quality check that otherwise we cannot do. And that gives us much better reliability. So what we're looking for in NEXPReS is the best of both worlds, both eVLBI and VLBI at the same time. So NEXPReS is a 3-year project funded by the EC to further develop the eVLBI we've pioneered in the NEXPReS project. And the goal is to have eVLBI in every VLBI operation. So not just the once a month eVLBI operations we're doing at the moment, but to do this for all the month-long observations or weeks-long observations that we have. So that's going to be quite a change. There are quite a number of institutes participating. I'm not going to list all of them. There are astronomical institutes, but also NRENs that are joining us in doing this research and building out this service. So to give you a little very schematic view of what we are planning to do is, you have the radio telescope over there, the data acquisition system, and then at the moment we either store it or we send it over the network. In NEXPReS we want to make it so that as we observe, we will store the data locally at the telescope, so it's very close to the source, so the chances of any mishaps are very small. And then we get as much over the network as we can, so that if the network is down, that's going to be 0. If the telescope has a poor connection or a slower connection, we'll get as much over it as we can. And we will store it at the correlator, and at the same time process it for at least doing the online quality checks on the data so we can telescope if things are going wrong. Then at the end of the observing, we start getting all the other data that we could not get through the network. We do that either by the old-fashioned way of mailing disk around, or by using the network to transfer the rest of the data until we have all the data for that particular observation complete. Then we will rerun the correlation again through our systems and get the best quality image that is possible with the telescopes that we've been using. So NEXPReS has a number of work packages. The first 4 are management work packages such as communications and the science advisory group and the EVN NREN meeting that some of you have been invited to next week. The next 2 are service activities. So cloud correlation is basically about correlating the data as you get it and then recorrelating it again. High bandwidth on demand is the same thing Hanno already talked about. Is using the new bandwidth on demand services for connecting to radio telescopes, and I'll talk a little bit more about it later on. Work package 7 is computing in a shared infrastructure. We are using our own custom-built correlators because the processing we do is fairly different from what a grid-based system does, for instance. And we are going to investigate more in how to make it different, because grid systems usually work in a sort of a batch mode, where you first transfer the data and then you process it. And that is a lot of overhead, given the fact that for eVLBI, the amount of operations is very large, but the amount of operations per incoming bit is very small. The reason, of course, is that we have an awful lot of bits coming in. So that doesn't make it very suitable for regular grid-based computing, but those resources can be used in different means, and that's one of the things that will be researched in work package 7. And in work package 8, we will looking at high bandwidth, high capacity, real-time storage, where we can catch the data at the telescope as the observation is happening, and then later on send it to GÉANT and replay it there from the same kind of storage as well. So a little bit more on bandwidth on demand. eVLBI is a little bit of an odd service on the network. It's not TCP based, it's UDP based. We simply It either runs at 0 bits per second when it's off, or it runs at the full rate, whichever rate we set. The highest rate at the moment we can do is 1024 megabits per second. And it's important for us to use jumbo frames as well, because otherwise the receiving systems actually will not be able to keep up. So where possible, we use dedicated network resources, such as light paths and VLANs. One of the reasons is that, in a sense, we do not play nice with TCP stacks. We do not do backoff. We simply keep sending the data if there's enough capacity. The other reason is that, although a stream at this moment of 1024 megabit for most NRANs should be fairly normal to deal with, especially in Holland, all these streams come together. And at this point, we are doing 1024 megabit, but in the near future, we hope to go to 4 gigabit per second and later even 10 gigabit per second. And it is well known that routed networks become very expensive if you start to scale them for only the highest capacity. It becomes much more useful to use things like light paths. At the moment, we have a completely static network, as I showed a few slides earlier, which is mainly for a reason of convenience, because setting up a light path used to be sending out lots of emails to people, talking to people, phoning them, getting the path set up, hop by hop over the different NRANs. Fortunately, all the NRANs actually take care of doing that for us. And then in the end, you have to test it, and it is so much work for them to set up a light path that you don't bother taking it down until the next observation. But this is, of course, an inefficient use of the networking resources that you have, and of the networking resources that you have. And it would be much more convenient and also flexible if we were able to use bandwidth on demand to automatically only use the connectivity and the bandwidth when we use it, when we need it, and then tear it down again. It also means that we can reuse the same ports on our networking equipment for different telescopes. And it also means that the international capacity is available for other projects when we don't need it. So most NRANs, or a lot of NRANs, have been deploying bandwidth on demand services within their own network. There is quite a list of different bandwidth on demand systems around the globe. And interdomain bandwidth on demand is really a new development. It has been demonstrated by GLIF in the automated goal project, for instance, in the GLIF meeting at CERN last year. And there's going to be interworking between all the different bandwidth on demand systems. So work package 6, high bandwidth on demand, has a number of tasks that we are dividing the work in. Integrating eVLBI with bandwidth on demand, which is basically the thing I just showed. Using it for our eVLBI operations. Task 2, Hanno, so to say, is also research bandwidth on demand for using it for transferring data between LOFAR long-time archive sites. And we also want to be able to test and validate the paths before we start putting actual astronomical data from actual telescopes on it. And the fourth task is to go to higher speeds on bandwidth on demand, international paths. Most of the NRANs are able to do this in their own network, but we want to be able to go from Netherlands, from SurfNet, through Netherlight, through Autobahn or GÉANT, or to telescopes, because as you saw at the maps earlier, these telescopes are spread out all over the world. The OGF NSI group is releasing their standard. It should already have been released. They are still working on it. We're hoping to see it real soon, because it will not only be implemented by OpenDirect and OSCARS and Autobahn and the others. We will also implement our own NSI agent to talk to all these systems using the NSI protocol, to request bandwidth, to set up paths, and we want to combine it with scheduling our telescope time, request and schedule the bandwidth, and have a user interface for a human scheduler to use this system and to both manage it and to plan in ahead both your telescope time, which is very scarce, but also your networking time. And, my last slide, the future of the EVN, some of the developments that are going on at the moment. More telescopes are joining. Van Spiel's telescope has been in restoration for a long time. I spoke to some of you about that yesterday. This is a new radio telescope in Sardinia that's being built, 64 meters in diameter. This is the moment that they actually placed the dish on the supporting structure. And on the left, you see something called the Uniboard. The Uniboard is another project that GÉANT is doing together with Astron and a number of astronomical institutes, where we basically try to make a universal building block for astronomical signal processing. What you see here is a cage with 4 times SFP+, and there should be 4 of these gives you 16 times 10 gigabit fiber connections into it. Then you have 4 FPGAs. These are the fastest FPGAs we could buy last year from Altera. Each has 1288 hardware multiplier that can each run at about 400 megahertz. So the actual processing capacity of this is enormous, and a single of these boards is actually able to replace our current correlator and get more capacity out of it. So it will be able to handle more telescopes or more bandwidth in more accuracy than our current system can. And we want to go to, and that is also going to allow us to do higher observing bandwidths like 4 gigabit per station, 10 gigabit per station. At the moment, I see Lars going, oh no. You know we're planning and hoping to do these things. And this is the way for us to do that. This equipment will not only be at GÉANT for correlating the data at the telescopes, it will also be used at telescopes for processing the data and getting it ready to get on the network. It's being used for pulsar research and other stuff, where basically this is able to outperform a complete cluster with close to 1,000 compute nodes for just the particular application that we are having. And this is a little shot of how the processing room looks at GÉANT with all the disk packs in the drives and the central network equipment we have over here and the operator console. And I'd like to thank you for the attention and ask for questions.
Thanks a lot, Paul. There's a question over here.
Well, I'm a bit of a hardware nut as well. So the Uniboard thing is very interesting. 2 questions about it. I guess the actual design is an open source project.
Yes, you can find it on the Uniboard project site. I can give you a link to it.
Cool. And the other question is, how did you actually find a party to actually make that board? Because it's very, very custom, I would say.
Yeah, it's completely custom, of course. Well, I don't think I should actually start giving company names here, but it's actually been done by a Dutch company that is also doing stuff for LOFAR, and most of the testing and design is done in the Netherlands, and production is done partly in China and partly in the Netherlands. And we've just received our first set of 10 Uniboards that will go to the 10 different partners in the project. So GÉANT has one, Astron will have one, and partners in the UK and France and other countries will each have their own board. They will each get they are each writing their own firmware already, and the firmware is going to be open source. I'm not completely sure if the board design is fully open source. Part of it, and the firmware is open source up to a limit because you will need the FPGA vendor's tool to implement it.
Okay.
Any other questions? So being a network provider, I'm always a little scared when I hear these things, so I'd like to ask about...
we like scaring you.
Yeah, of course. Timing, so what's the both for getting to 4 gig and 10 gig, but in particular for getting the bandwidth on demand activities working? Well,
bandwidth on demand, we hope to have our first demo, which is actually going through your network, as you know, at I think somewhere the end of next year, a little bit earlier, or after actually the Glyph people have demonstrated this in Rio. Shortly thereafter, we would hope to be able to at least do a test bandwidth on demand from the Onsala telescope to GÉANT.
Okay.
And that's going to be at just 1 gigabit. That's not yet going to be at the higher speeds.
Okay.
And within the timeline of the 3-year NEXPReS project, the 10 gigabit per second is actually 10 gigabit bandwidth on demand is actually almost at the end of the project, and I think the 4 gigabit is somewhere halfway next year or so.
Okay. Okay. Thank you very much, Paul.
Okay.
Thank you.
So for our final presentation, we have Domenico Vicinanza from Dante, where he works as an international relations and project support officer. Domenico has also worked at CERN, worked on the LCG, support for that, for the computing grid, so he's got a lot of experience in supporting advanced users and their advanced applications. And he's going to talk to us today about how to support these kind of things in cross and pan-European projects and the complications that brings.
Thank you very much, Lars. Thank you, ladies and gentlemen, for being here this afternoon. And I would like to start immediately having a quick look at a few of the interesting things that have happened in the research world in the past 10, 15 years. So I think the most important thing is that we are looking at a slightly different way of collaborate among scientists, researchers in the world. I think we can see an increasingly international collaboration between researchers, students, and people that are involved in the science. This is gradually leading to a more efficient way of sharing experiences, resources, facilities, and probably the global result of this more efficient way of sharing what we have in our local laboratories is a more sustainable way of doing research. I don't need to replicate a data center if I have an efficient network connection that allows my user to go there and retrieve the data I need. So all this leads towards something which is more sustainable, that scales better. Another thing that is happening is an increasing number of advanced applications that research and education is currently using for different purposes. I just listed 3 of them. So the first one is to model complex systems, or to process and analyze experimental results. There's been a few presentations about that this morning and this afternoon. The third use case is what the speakers said this afternoon mentioned. It was related to delivering data in real time across really big distances. So connecting different locations around the world and delivering real-time data. So we have some precise research needs that are calling for quite precise network characteristics, network requirements. Real time is the first one. It comes from the new demanding application that needs to be accessed from different locations in the world, but also high bandwidth, as we have seen this afternoon, low latency, low jitter, so stable network, and no losses. So the standard internet is not enough to answer to this question, to meet those expectations. So that's why, more or less 15 years ago, research and education networks started to appear in the world. So countries started to build dedicated network for research and for education. And that's why also something to bring those networks together and create a seamless networking infrastructure was born, like GÉANT in this case. The global purpose was to offer a global connectivity which was dedicated to research and to education, available for all the researchers, for all the people that were needing those advanced applications. So research and education network are basically there to answer really 2 quite interesting use cases. The first one is providing access to unique resources. For example, some quite particular, quite unique supercomputing center that for example, has thousands of users across the world, or having some access to some large database. The other use case is probably even more interesting, which is building such unique resources, combining together, joining together local smaller resources and making them interacting and allowing a synergic interaction among them. This is the concept behind grid computing, cloud computing, distributed databases and storage. And so together, the aim is to respond to the requirements of the most advanced research applications. So, just a few words about GÉANT. I know that most of you know almost everything about this pan-European backbone. Just would like to remind a few numbers. So the total users that are connected by the NEXPReS and GÉANT is almost 40 million, so covering 8,000 institutions and more than 40 countries. So it makes an ideal infrastructure to build advanced applications, share data, and start doing real research. And this is also because we are able to provide high capacity thanks to an over-provisioning of the network, low latency, low jitter. So complex application can find in the NEXPReS and GÉANT a natural place to be. Collaboration is then enabled. We have video conferencing, we have distributed computing, and so on. And here is a picture of displaying how GÉANT and the European network research and education networks can be connected to, or actually are connected to, the other research and education network in the world. And I particularly like this picture because it also mentions a few projects that are based in different locations, showing that what we have here is not just a mesh of cables. It's actually something that enables some real usage, some real user community to be there and to actually do their job. And so we currently are supporting more than 30 international projects using the network. And the main purpose is to help them to improve their network experience and hopefully to make their life easier. And to do that, GÉANT has a dedicated team, which is part of the network activity number 4, which is dedicated to liaison and support. And it is namely its task 3, which is devoted to project liaison. And this dedicated group in GÉANT, which is the project liaison and support team, is there as a main point of contact for any external project organization that is wishing to use the GÉANT network or is already using the GÉANT network and like to have something more. So what does the project liaison team do? It mainly provides assistance to support project initiatives, organization to facilitate and encourage the use of the research and education network. But it also presents the advanced services the NEXPReS and GÉANT is able to offer them. It is helping them to understand the network needs, and importantly, to match their needs with what the NEXPReS and GÉANT can offer to them. And how it is doing that? In many different ways. Participating face-to-face meeting, video conferences, phone calls with the project. And if you like, the team itself is kind of interface or sometimes even interpreter between two quite different group of people. So we have researchers, scientists on side, and network operators on the other side. And our main task is to let them talk their native languages and interpreting and translating the things between the two teams. So understanding research requirements and translating them into network characteristics and network specifications, and translating network services into actual benefits for users and for scientists. And so to illustrate how we are actually doing that in a practical way, I have 4 brief examples describing how we are operating in 4 different research environments, 4 different dealing with 4 different research communities. The first one is radio astronomy we were talking about before, and this is it is related to a 4 gigabit connection between Onsala in Sweden and Jodrell in the UK. Radio astronomy is pretty interesting for us because it has quite strict network requirements to meet: high throughput, stable flow, low latency, no losses. And so this 4 gigabit circuit was the result of a collaboration of of different entrants. You can see the topology of the circuit here. And it was made of different trunks. You can see 4 gigabit Ethernet path over TSS NordNet. We have GÉANT Plus with SDH. We have GÉANT with optical transmission. And we have finally the link to Trodel Bank. And what happened? So you see that theoretically all the links were able to support 4 gigabit connection. Actually, doing the actual test, we saw that the maximum throughput was only 3.78 gigabits per second, because of a 10% packet loss. We started some investigation to see where those packets were lost in the network, and we doing some detailed analysis. And actually, you can see here one of the graphs that allowed us to understand what was happening. This is the inter-packet arrival time as a function of the received time. You can see those little dots sitting here at 6 microseconds. So this means that the packets were actually delivered from the TSS to the MCC in Copenhagen, not as a continuous flow of 4 gigabits, but as a bunch of 10 gigabits per second line speed, then waiting a little bit, and then another bunch. The waiting part, you can see here, so this dot here is representing the fact that after a burst was waiting, then bursting again, waiting, bursting again, waiting. And so the average was actually 4 gigabits per second. But the weight was delivered was through burst. So what was the consequence? Well, the Alcatel MCC ingress buffer in Copenhagen was only 75 kilobytes. It was not able to cope with the burst. So packets were dropped. So this solution was found, and actually NordNet solved the problem using SDH to connect to the Alcatel MCC in Copenhagen, and the problem was solved. But an important thing happened, apart from solving the problem, is that we were able to feed that information back to the vendor and having actually the buffer modified. And this was probably removed some other potential problem in future. Another thing we were able to do, and within the NEXPReS collaboration, was actually measuring for the first time the jitter on that path. And the interesting thing is that the jitter was really, really small, was 60 microseconds with a really narrow peak. So you can see here that the tail was at 1,000 times smaller than the actual value. Another example, it happened something like 15 months ago when we, as a part of the acceptance test for a link between Europe and Singapore going via India, Mumbai, and the problem to solve there was trying to understand what was the effect of low levels, optical level switchover that was happening every time a fiber cut was detected from the actual user point of view. So imagine that there was a low-level optical error here, for example. This was affecting a data transfer between the user here and the user here. So what we did was simulating a continuous flow of data across that link, as a user is continuously sending data from one side to the other. And you can see here that's the bandwidth as a function of the time. And that's what happened when there was a switchover. So the connection was not teared down. The connection stayed alive. The TCP transmission stayed alive. The data transfer continued. The only thing that happened was that the actual bandwidth available dropped down to 200 megabit per second for 20 seconds, and then it went up again. Another test we did was intentionally breaking the link and trying to see if the rerouting was actually affecting any data transfer, anything the user could actually detect from his point of view. And you can see this was the bandwidth before the rerouting. We cut the route, so the bandwidth went down a little bit and then up again to the new route. So again, the connection was not lost. If the user were doing a really delicate, really important data transfer was not interrupted. So it continued, and the only thing the user was experiencing is just a slight decreasing in the connection speed for just 10-20 seconds. Another example. This is in a slightly different environment. So dealing with multicast, we had an interesting proof of concept we did in collaboration with EUMETSAT, the European Organization for the Exploitation of Meteorological Satellites. And they were interested in learning something more about the possibility of using multicast for high bandwidth data transfer on terrestrial network. And so we did a proof of concept in collaboration with them. And this is what we did to test if the network was actually able to cope with high bandwidth multicast transmission. We set in London a server to generate some multicast traffic, and we had a receiver in London, one in Amsterdam, and another one in Prague. And our first phase was just trying to send some well-known traffic through those 3 points and trying to understand what was happening. This phase was successful. We went to the second phase, and we installed some EUMETSAT equipment in the POP. And we had some real EUMETSAT data traffic going there. And so this led to a real measurement, using real data and real EUMETSAT applications across the network. At each site, we were measuring throughput, packet loss, and inter-packet arrival time. The result, the network was able to sustain a stable throughput up to 500 megabits per second. No packets was lost once the multicast tree was established. We test many simultaneous flows. I think this graph here is about five different flows, and we measured the jitter, and the measurement was quite satisfying, just 11 microseconds. My last examples, my last group of slides, is related to a link assessment was done for again another quite different field. We are now talking about arts and humanities, and the event was the GÉANT launch event. Some of you were there in Stockholm in December 2009, and we would like to find something quite interesting from the network point of view, but which was also able to show in a practical way how the network can enable something new, something original. So we decided to organize distributed music and dance performance with musicians sitting in Stockholm and actually dancers in Kuala Lumpur, and using the network to send the music to the dancers in Malaysia and sending the video of the dancer back to Sweden. So to give the impression that we're actually dancing and playing in the same virtual space, in the same virtual location. The whole thing was the result of a nice collaboration between a few NEXPReS. So the museum where we were playing was connected with optical fiber to Sunet, the Swedish NEXPReS. Then the music capture was traveling to London, passing through the Nordnet Link and GÉANT, and then going to Tain, using the link that you've seen in the seen before, and then from Singapore going to Kuala Lumpur via the Spain and the Malaysian migrant. The dance was captured using a digital camera in Malaysia and sent back to the same link to Sweden. So quite strict requirements, in particular about packet loss. We couldn't have packet loss, in particular for the audio transmission. Packet loss was resulting in clicks in the audio system. Low latency, a very low jitter. That's particularly important for the video part, to have something nice and not pixelized. The test result, you can see something here. We got 0 packet loss. The collaboration was working really, really well. So also taking into account the time difference that we had there. So we got rehearsals with people actually having to wake up in the middle of the night, doing rehearsal, and then going to sleep, and then the morning after continuing doing tests and so on. No packet loss. Everything was absolutely fine. We were able to transmit and receive at line speed, and you can see here the result of the collaboration. So playing here in Stockholm, and this is a snapshot of the video coming from Kuala Lumpur. And if you like to see the whole performance, you can go on the GÉANT.net, and you can find the video there. Fine. Summarizing, so we are going to have an increasingly cross-border international way of collaborating, of exchanging data, information, experiences, science, research, education, requiring and calling for new applications that are able to meet their requirements. And in turn, those applications requiring some advanced, dedicated networking. And so this is what the ENRANS and GÉANT are actually doing in the past 15 years, working together, working synergically. And within GÉANT in particular, a dedicated team started to work, liaising directly one by one with those projects. So acting as an interface, trying to be able to speak the researcher's language and converting requirements into network specification, and trying to help a user project to meet their expectations, and continuously working together, trying to find a better way to work, to exchange information, and to improve the research. And that's everything. Thank you very much.
Any questions for Domenico? One here.
Hello. I was hearing this during the speech, and now the last part. I was thinking, on my NRAN, I have scientists. They have projects, but I believe that they never heard from you, or they don't know that GÉANT has this kind of service. How do you reach the researchers?
That's a good question. We try to do 2 things, basically. First of all, trying to liaise with the entrants, trying to let them know what we can offer, and let them know, this connectivity service. We know that you have some projects connected to you. They might be interested in knowing this, and this. Another thing we are doing is actually liaising directly with organizations and projects, so meeting them, or also proactively, so that you might be interested in knowing that. The other thing another way we are interacting with, we are starting the interaction is actually inviting projects so to talk directly to us. And actually, this was happening for I think more than half of them. They contacted directly us, so they knew about us, and they start just sending an email or filling a form on the website saying that I'm I'm a project based here. I'm interested in using the research and education network. I know it's good. How should I keep this forward? And so we have a dedicated team to start the contacts and then following up with the NEXPRES and with GÉANT networking guys.
Okay.
Any other questions? I think I have a question there, then I follow a bit up to what Rui was asking. I mean, you talked a bit about, or mentioned some quite challenging technical problems and the good work that's been done to investigate those, but I would imagine that many of the problems you're facing are really not technical, but community problems, communications problem, how to talk to the right people, how to make the Portuguese NREN aware that you are there, that you can help them support their users and all that. And so all the challenges, I would like to ask you about the challenge. What kind of challenges are you facing in that? Are you facing resistance from the NRENs? What would be improvements to the process that could happen that would make this easier to support pan-European projects? Can we do this better?
Well, I think the first things that we need to do is trying to improve the communication. So improving the channel that we have between GÉANT, the NEXPRES, and the final users. There are many possible ways to do that, and I think that we really need to improve this communication, increasing the awareness about the fact that there is a dedicated connectivity or dedicated a set of connectivity services that might be interesting for many of the projects. We also have quite a lot of users that are using every day the GÉANT network and the NEXPRES networks, and they don't know. In particular, for example, grid-related projects, they can see the grid part, but they don't know that there is something else behind, which is the connectivity the NEXPRES and GÉANT is providing. It is something if they like, they can use in a better way. We can also help with troubleshooting or tuning the end host, for example, to improve their connectivity end-to-end.
So you could say that a major challenge is involving more the support staff at the NRENs in this activity, so that they know that you're there and can help the end users. Right. Okay. Any further questions to Domenico? No? Well, thank you very much, Domenico.
Thank you very much.
Then, before I let you go, just briefly like to remind you that this upcoming coffee break is your chance to go and meet the students who have done the students poster competition. There's 10 of them, and I've seen all of them. They're quite good, some of them, and I think you should go and look at them. I'd also like to remind you that this evening is the gala dinner, of course, of the conference, and because we're using trams to get to the venue, there is only 3 opportunities to catch the transport, and you have to meet in the lobby to meet the guy downstairs at either 7:15, 7, or 7:15. The trams have to leave on time because otherwise they can't be on the tracks. So have fun.